and is based on joint work that we've been doing for many years. We've now produced 2 papers on this, and I'll report mainly on the second paper, but also parts of the first. So for your convenience, I'll post the stochastic PD up here as much as I can. What you see here is we have a heat equation plus a noise term, which for convenience, I'll just show the multiplicative noise case here. There's a slightly larger result that one can present, and there's also a drift, nonlinear drift term, which again, for convenience, I'll have the Allen-Kohn nonlinearity here. The equation takes place on the interval -1, 1, which I'll think of as a torus by wrapping it around. The white noise is denoted by W dot. And there's a parameter here which you could absorb into the model if you wanted, and we won't. We think of it as a noise level. So you think of this as a tuning parameter. You can tune it up and down to see the effect of the noise on the underlying model. Okay. The only other thing that I have to mention is the initial data. The initial data, psi 0, is assumed to be a continuous non-negative function. And if it's random, it's going to be then independent of the noise. So here's a, I don't know how well this shows up, but here's a simulation of the model done by Zimmerman et al. A few years ago. What you see here is the x variable in the horizontal direction, evolving in time. That's in the y-axis, direction of the y-axis. And what they claim is what you're seeing is the evolution of the 0 set. That's the black. I believe what they mean are the small values of the voids. Nevertheless, what you're seeing is the multifractal structure of the solution. And what causes this is what they call spatiotemporal intermittency, which is the effect of this multiplication right here, highlighted in the equation. And they actually make predictions about the solution, some of which one of which in particular we'll discuss today. So before we do, here's a theorem about existence and well-posedness, which we add in for completeness sake. So here's the first result is that this stochastic PDE has in fact a unique solution. The solution is a non-negative continuous function. In fact, the evolution of the solution as a function of time is a Feller process on the space of continuous functions. And then the third part, and this was why I was being a little bit careful about my statement about the 0 set, is that the 0 set is in fact empty. There's no 0 to the solution, provided that the initial data has non-zero values. So unless the initial data is identically equal to 0, the solution will be strictly positive at all positive times. There are many, of course, results of this type, and I, for example, refer to Sandra Chirai's work here. But as I said, there really are many other results as well. The main purpose today is to discuss the existence of an invariant measure and uniqueness of an invariant measure. If I have time, I'll say something about what it looks like. I probably won't. So just to be sure, an invariant measure is a measure mu such that if you start your initial data according to that measure, then at all times you will follow that measure. So existence is not a problem because you can see this is the equation right here. You can see that if you start at 0, you always remain at 0. If psi of 0 is 0, then psi is 0. 0 solves this equation. Another way to say that is the point mass on the 0 function is an invariant measure. So really the question here is whether or not that invariant measure is unique. And that's maybe the bulk of today's statement, is that there are two non-random, strictly positive numbers, lambda1 and lambda2, or lambda1 and lambda0, such that if lambda is greater than the larger of the two, then in fact you have a unique invariant measure. So if you should think of this as if there's enough noise in the system, then the invariant measure is in fact unique. And conversely, as you might imagine, I'll come to that maybe later, if there isn't sufficiently sufficient amount of noise, if lambda is less than lambda0, then there's a different invariant measure, mu plus. It lives on, is unique. It lives on the set of probability measures on a space of functions that are Helder alpha for any alpha less than a half, kind of like regularity of Brownian motion. The functions on which it lives are strictly positive everywhere, consistent with the solution of the equation. And any other invariant measure is a convex combination of it and delta function on 0. So the two extremals are the trivial one, delta function on 0, and this other one, mu plus. So that's the bulk of the statement. If this equation is noisy, then there's a unique invariant measure. If the equation is not, then there are infinitely many invariant measures. The proof produces some information about the invariant measure as well. I sort of alluded to properties of invariant measures quickly before. So here's one. The tails of the invariant measure are stretched exponentials. So if you look at e to the third root of x, then apply any of the C alpha norms of the function to that, the invariant measure integrates that. The invariant measure is the non-trivial one, of course. Delta function also integrates that, but in a trivial way. Therefore, so do all invariant measures in the infinite case. And finally, another property that you can say, this is to be expected, is that the invariant measure corresponds to an ergodic theorem. And the ergodic theorem holds in total variation. I do want to emphasize that this is known, that at least not maybe all, but a lot of this is known in the sense that Zimmerman et al. Predicted this result, especially the non-uniqueness part, which is noteworthy. And they derived this with computer simulations and experiments. Of course, we proved that they're right, or a suitable version of what they say is right. The second statement that I'm making here is that this nonlinearity here, the Allen-Kohn type, can be replaced with other types of nonlinearities. So for example, you can replace it with Fisher KPP, that's this one here. And pretty much everything in purple, this theorem here is correct, and this is the same statement, except maybe this one result about the tails has to be adjusted a little bit to a statement that it still has stretched exponentials, but it integrates e to x to the quarter rather than e to the x to the third. And in fact, as I mentioned, this polynomial term can be replaced with lots of other potentials. This one also can be replaced with many other functions, as long as the moments have an intermittency property, which is that the moments of the solution without the drift grow extremely fast on different scales. So the kth moment is much, much larger than k-1 moment as t goes to infinity. Okay, so maybe if there are no questions, I'll be happy to say a few more things about some properties and then maybe one or two lines about proofs. Okay, I hope this statement was relatively clear. Assuming that, then in fact, one can say even more about the properties of the invariant measure. So here's one. I might have mentioned that this, when lambda is large, there's this other invariant measure mu plus. I might have mentioned that it lives on a space of continuous functions that are strictly positive. In fact, you can get a bound. So you can show that if this tuning parameter lambda is sufficiently small, not only does this other invariant measure exist, in fact, probability that you ever go below epsilon is less than epsilon to theta for any given theta. So here's the exact statement. For every theta, there exists a lambda theta small enough such that if the level of the noise goes below that, then the measure of the set of functions that ever go below epsilon decays like epsilon to theta or less. This is tantalizingly close to saying theta equals 1 is acceptable, in which case one might even think that the infimum of the functions has a density. We don't know how to prove that. I also might have mentioned that this invariant measure mu plus lives on the space of functions that are held or continuous of order alpha for any alpha less than a half, kind of like the regularity of Brownian motion. In fact, that's sharp. The measure of the space of C half is 0. And just to make the analogies stronger with Brownian motion, McKean proved in 55 that if you look at Brownian motion, it doubles the dimension of every set. So specifically, if you take a deterministic non-random set G and look at the image of G under Brownian motion, so if you pick omega according to Wiener measure, then the dimension of the image, if you ignore this one minimum, is twice the dimension of G, doubles the dimension of every set. The only reason you have a one minimum is if you can imagine you have a set G that has Hausdorff dimension 2/3, then Brownian motion can't map it to a set of dimension 4/3. That would be 2 times 2/3, simply because there are no 4/3 dimensional sets in R1. So then the dimension becomes 1, and this one minimum kicks in. And the statement here is that exactly the same theorem is true for this invariant measure. Maybe I'll ask the question anyway before we go on, and that is that this of course shows that the paths that this invariant measure picks locally look very much like Brownian motion, except they're strictly positive. So one might imagine they would probably be looking at things like e to a Brownian motion plus a secondary term. We don't know how to prove that. We also don't know how to prove whether or not there's a phase transition. So this other invariant measure about which this theorem says a few things really only exists if lambda is sufficiently large. If lambda is small, I already mentioned we have only the trivial invariant measure. So one might ask, is there a phase transition? Usually when problems of this type have phase transition, is because there's some monotonicity in the problem. I'm not aware of any monotonicity, and to their credit, Zimmerman et al. Also don't ask whether or not or make a claim on whether or not there is a phase transition. It is possible that for the model, the way I've written it here, there really is a sharp phase transition. So that means that there's a critical lambda such that if you're above that, then there's a unique invariant measure. If you're below that, there are infinitely many. But that, if that's true, that would require work, additional work, of course. So maybe I'll say a few things about the proof. So the proof is in two stages. One, we have to show that if the invariant measure is, sorry, if the level of the noise is small, the invariant measure is unique. And then sort of conversely, if you will, if the level of the noise is large, the invariant measure is non-unique. So for the first half, here's how the argument goes. You look at the drift term here. And remember that this psi is positive. So the drift is bounded above by just psi. And the comparison theorem for SPDs says, well, if the drift is less than psi, this other drift, linear drift, then the solution is less than the solution to the same equation if we replace the drift by the larger one. And this is a linear stochastic PD. The initial data remains the same. So the solution of the equation that we're interested in is bounded above by the solution of this equation. No nonlinearities. And of course, it's bounded below by 0. So it's sandwiched between these two barriers. Now you perform a standard transformation. You multiply the solution to this SPD by e to the minus t, and you get an SPD that might be more familiar to you. It's just the linear stochastic heat equation or the parabolic Anderson model. And we know a lot about this one. Again, the same initial data. And a few years, so this was actually the first part of this project. A few years ago, we proved that the solution to this equation goes to 0 exponentially fast. So there's a universal constant C such that the solution here is less than e to the minus c lambda to the fourth. Lambda is this constant here times t uniformly. So if the solution here is less than e to the minus c lambda to the fourth times t, if you multiply by e to the t, you get a bound for this solution. So if you multiply that by t, you pick up an additional 1 here in the exponent. Okay. And of course, v is a bit bigger than psi, so the same statement is true for psi. And now you can see that if lambda is sufficiently large, then this is negative. And what that means is that 0 is an exponential attractor for the solution to this equation if lambda is sufficiently large. So the solution goes to 0 exponentially fast in the soup topology, soup norm topology. And so, of course, it's not hard to imagine from there that because that's true, in fact, 0 is the invariant function. So there's a unique invariant measure. So that's half of the argument. Is based on this dissipation result. For the other half, I think even if everything worked on time, I wouldn't be able to show you the other half fully, but I can show you the argument that ultimately led to a proof. This argument itself isn't really fully rigorizable. Nonetheless, it motivates a proof that is. So for the purposes of exposition, suppose you really did have only one invariant measure. So the goal would be to show that if there's only one invariant measure, then lambda would be in fact sufficiently large. Now, it's not a stretch of the imagination to assume that if delta zero is the only invariant measure, then zero is an exponential attractor. Let's say it's an attractor. So you actually go to zero in the soup norm. Again, you stretch a little bit more the imagination, say, well, okay, so of course that means that the solution psi tx is approximately zero when t is very large, uniformly in all the x variables. Therefore, psi minus psi cubed, the nonlinearity, is approximately equal to psi when t is large. So of course that's all true and easily regularizable, except for this part. The part that might not be fully true is that one can imagine, well, therefore, since the two nonlinearities are equal, the two SPDs are very close. So this SPD would be very close to this SPDE when t is large. And the problem with this statement is that SPDs are non-local objects. And so it's really not, as stated, it's really not true at this level of generality. Nonetheless, you can imagine it might be on a suitable scale true. And so we're back to this old SPD, old meaning on the previous slide, this SPD that I mentioned in the analysis of the first half of the top one. So a few years ago, we proved a secondary statement about the dissipation of this SPD. So on the previous slide, I mentioned that eventually as t goes to infinity, the solution is less than e to the t minus ct lambda to the fourth. And what I'm staying here is that there's also a lower bound. Namely, you can find a constant capital C such that by replacing what I called little c with capital C, you can flip that inequality. And in the strongest possible sense, you might notice there's an infimum here. So it's not a soup norm, it's actually the infimum. So the solution is bounded everywhere from below asymptotically by e to the t minus ct lambda to the fourth. And so you can turn around the previous argument and say, therefore, if lambda is sufficiently small, this thing becomes positive, and therefore the lim-inf becomes positive. And there is this approximation, v is almost psi, so the solution here must have maybe the same property. And that would tell you that your assumption that zero is an attractor is false. You stay away from zero at an exponential rate. The part, of course, that's somewhat difficult to manage is step one. And so this is not quite what we prove. But if this argument is true, you can sort of see why there are obvious generalities here. The role of psi cubed here is kind of minimal, in fact. In the upper bound, we just removed it. And in the lower bound, we said, well, if psi is close to zero, psi cubed is much, much smaller than psi, and therefore we can remove it. So in fact, all of that is true. And that's the reason why you can, instead of psi cubed, put any other function that you would like amongst the very large class of potentials. So again, even though the proof, this argument isn't really a proof, it does show you quite a bit about the general structure of the equation. I think on this note, I will stop. I'm already 10 minutes late. I do apologize for being late. Box gave me an interesting morning today, but I'm happy it finally worked. I'd be happy to answer some questions if there are any.
Thank you for your very nice talk. So I suggest we move on with Oleg's discussion first before we take any questions, and then if there are any remaining questions, we can take them at the end. So Oleg, please.
Yeah, hello.
Yeah.
Let's see. Let me do full screen.
Not yet.
Opa. Can you see me? Can you see my full screen?
Yeah. Yes.
Okay, perfect. So yeah, thank you very much. Thank you very much, Devar, for an opportunity to discuss your very interesting paper. I think it's a very beautiful result. So I will just do a quick discussion of Devar's result, and then I'll present some related problems, and then I will ask a couple of questions to Devar and to members of the audience. So, okay, so let me start by recalling some very basic results. Ergodic decomposition, so like very basic stuff about like Markov process 100-01. So let's say we have a Markov transition kernel P over some Polish space E, and then a set is called invariant. If we start in this set, then we always be in this set, right? So we have our state space E. This is my state space, and then I let's say have a set, so that if I start in this set, I can only be, my whole evolution can be in this set A. I will never be able to leave it. So such a set is called invariant. And then let's say we have an invariant probability measure for our Markov process, and then we call it ergodic. If it attaches to every invariant set, probability 0 or 1. Okay, so somehow it is concentrated like on this set. And then there is like a well-known result that we have a Markov transition kernel that has, I don't know, a lot of invariant measures, and they might not be, of course, like there is like not singular, like anything that can happen, but any two ergodic measures will be mutually singular, and any invariant probability measure will be like a convex combination of some ergodic invariant measures. Okay, so among all invariant measures, there are ergodic measures, which are somehow the edges of our convex stuff, and any invariant probability measure is like just a combination of them. And oops, 1 second. Okay, and so let us imagine, and so somehow this basic theorem tells us how one can try to show uniqueness of invariant probability measure. So let us say that there are two invariant probability measures for a Markov kernel, and then they all are supported in some invariant set A. But then by this theorem, there must be two ergodic measures on this set A. And if there are two ergodic, then they are mutually singular, right? So maybe let me just draw the picture. So let's say I have a set A, and let's say I want to show that I have a unique invariant measure with support on A. I assume the contrary. I assume that there are two invariant measures, but then there are two ergodic measures, which are mutually singular. So then it means that the invariant set A can be further split into, let's say, A1 and A2. And each of these guys, A1 and 2, is also invariant. And to show that this cannot happen, I just need to show that my process will explore these sets thoroughly enough. So that if I start at any point of my A, I will definitely be, let's say, visit any other point. So this would definitely be enough to show that this cannot happen. Now, this is the intuition. And usually, so this is done with a certain support theorem or some what is called accessibility conditions. There are many techniques. This is a little bit related to what Armen was explaining earlier in the morning. But what we also need to learn from this stuff, that in general, so if I have my state space E, then I can divide it into many invariant sets. And then on each set, there are two options. Or we have one ergodic invariant measure, or we have 0 ergodic invariant measures. And then any invariant probability measure would just be some convex combination of all of them. Okay, so this is like a general theory. Now let's go to practice. So what is the main result of Devar? So he considers this equation, and then he proves that this is a Feller-Markov process with state space of all continuous functions on a torus, which are not negative. And we can split this state space into two parts, exactly as I just showed you. So one is 0, and one is everything apart from 0. And then it is relatively clear that if you start at 0, then you will always stay at 0. And if you start not at 0, then you will never be exactly 0. Okay, and now we can apply the theorem that I just explained you before. So each of these two things is invariant set. Now on 0, it is clear that there is a unique invariant measure, just delta 0, just you always stay at 0. And then it is proved by Devar that on the complement of the C plus tau, by some support theorem and some coupling techniques, one can show that, that the protests explore this space thoroughly enough in the sense I just explained, so that it cannot be that there are two invariant measures on this set. And then, so in the end of the day, there are two opportunities. So here we always have one invariant measure, and here there are two options, one invariant measure or zero invariant measures. And in case there are zero invariant measures here, then okay, there is a unique invariant measure for the protest. And in case there is an ergodic invariant measure, then any other measure would be just a combination of delta 0 and whatever you got here, what was called mu plus. Right, so this is what I said here. Now, there is a lambda. So now everything depends on lambda. If my lambda is 0, then of course, for this deterministic equation, there is a second stable point, just 1, right? So if we start at 1, we always stay at 1. And so what is the result? That if lambda is 0 or small enough, then this is what will happen. That there will be this instability, that you will have two invariant measures for these equations. And if lambda is very large, then the equation will just goes to 0, and thus there will be no additional invariant probability. So this is the result of Devar. And what I found it's very interesting is to compare this with very recent paper of Martin Heira and Zelati. And they are in an opposite situation. So they study what is called stochastic Lorentz system. For us, it's not so important. So this is some SD. Two equations are deterministic, and in the third equation we have noise, and again intensity depends on lambda. Now this is also a failure Markov protest, but let us note something. If my x is 0 and if my y is 0, then what is my equation for x? X dot is 0, y dot is also 0, and then equation for z is just Ornstein-Uhlenbeck, because this term disappears. So somehow we have a similar setup. So the state space R3 can be divided into two parts. Either x and y are both zeros, or they are not zeros. And if lambda is 0, then there is a unique stable point 0. And this is a picture I stole from Martin and Zelati. You see this red guy. So if the noise is small, and this is this red guy, then you are attracted to 0. Okay. And if the noise is large, this is the blue thing, then you first are attracted, and then, you know, some stuff are going on. So the noise pushes you off from the attractor. And so it is, one can conjecture, and this is what is proven in this paper, that the situation here is the opposite. So what is the same? That again, on this set, there is a unique invariant measure. On the complement, there is no more than one invariant measure. So again, this Markov protest explores this set good enough. And now it's the opposite. So for small lambda, there is no invariant measure here. You will just go to 0. This is what happened in Devar with large lambda. And here the opposite, with large lambda, there will be one invariant probability. So in Devar's talk, you have instability, you have a PDE with two stable points, and then you add noise, and then things become unstable, they converge to 0. In the example of Martin and Zelati, it's the opposite. You have something stable, you have this Lorentz attractor, everything were converging to 0. And then if noise is large enough, then, okay, you have an invariant measure. And also very similar to Devar, Martin and Zelati, they cannot prove that you have a sharp transition. So what they proved is exactly the same. So for small lambdas, you have one measure. For large lambdas, you have two measures. What's going on in between is completely unclear. So if there is like one sharp point or two, this is not known. And the reason is exactly the same, that as Devar mentioned, there is no monotonicity in terms of lambda, so it's difficult to do any comparison here. And now let me very briefly talk about our recent paper with Mikhail Shoitso, where we suggested some new techniques for ergodicity, which we hope maybe can be useful here in the work of Devar to prove something new and something extra. Maybe they will be, at least I hope that they can be used to simplify some of the proofs of the current stuff, and maybe one can prove something more with that. actually it's known for quite far. This is the work of Shiga or Lechen, that this guy is order preserving. And what do I mean? That if you start this equation with two initial conditions, one above another, like this, and this is at time 0, and then at any other time t, with probability 1, the same structure will happen, right? So I launch this equation with the same noise, with two different initial conditions, and this has always happened. And okay, so one can introduce an order, so we can consider this as a Markov process with the state space L2, and I have a partial order on my L2. I say that one guy from L2 is bigger than another guy from L2 if this happens. And okay, well, and then one can show it's a general result. So it would mean that the same group corresponding to this process, which act from C plus to R. So if a function from C plus to R is increasing in this sense, then the semi-group, some PTF of F, transforms it also to increasing function. And this gives like a kind of orthogonal direction, orthogonal point of view to all this story, right? So Jonathan, Martin Glenn, Martin Heyer, and many other people, so they have lots of works regarding, they considered what's going on if a Markov process have a failure property, strong failure property, asymptotic strong failure property, and they all work, so failure is continuous to continuous, strong failure is bounded to continuous, and our observation with Mikhail is that it is interesting to consider stuff which maps increasing function to increasing functions. This is completely orthogonal from this story. And then it turned out, so that relatively general result holds, that if you have a Markov process which is order preserving, then there is only one, so there are lots of technical stuff you need to check, but this is not so important. But there is one key condition you need to check. So this is our state space E. And okay, we need to check, and this is, let's say, a ball. And then I need to check, and then let's say I have some point. So in our SPD case, the point is something is identically 0. So I need to check that with some probability. So if I have two solutions, so okay, I will formulate it like this. So if I have two solutions and one was less than another in this order, then there is a coupling which will switch them. Okay, so this was, so it's not, of course, it cannot be deterministic coupling. There should be some coupling which should change, should break the order with very small probability. And once you can construct such a coupling, then that's it. Then you have a unique invariant measure and life is good. And I don't have a lot of time. Let me very briefly show. So for example, what we did with Mikhail, so we consider reaction diffusion equation with finitely many noises. And we were able to show that, okay, that condition holds. So you have here exponential convergence to unique invariant measure and even synchronization by noise. So if you start your two solutions from different points, that not only the Wasserstein distance, so Wasserstein convergence tells you that there exists a coupling. And this tells you that a very natural just coupling with the same noise will also converge. So any two solutions will somehow converge one to another. And this is actually a very interesting complement and some extension of the work of Heyer and Mattingly of 2011. So their works, they had totally different point of view. So they had a huge class of equation, and then they showed that if this noise satisfies some Fermat condition, then life is good. And our point with Mikhail is that for very specific subclass, which of SPDs which are order preserving, you can actually prove much more if you take this order preservation into account. And okay, and so now let me maybe finish. Okay, and so just to recall you, so okay, so for this guy, order preservation is known, and then the question is, so is it useful and what can we do? So maybe I will start with a very basic question to Davar, because I'm not sure what's going on in finite dimension, because we can consider the same stuff as an SD. And so my question to Davar would be, is it known that here you have a critical guy lambda or not? And then the second thing I would like to discuss is, okay, so whether there is a hope. So you see, so from what I understood, they didn't prove convergence in Wasserstein metric. They proved something like a weaker result. So either any hope for convergence in the Wasserstein metric. There is a connection with the talk of Yuri tomorrow, because he will also talk about, so he will study discrete stochastic heat equation with discrete space. And he will also be using order preservation property for ergodicity, but in a different way. And what is very important, he will not be using this switching condition, which is sometimes annoying to check. And so the question would be whether his technique, or whether like how the most general you can go. So let's say you have a order preserving Markov process. What is the weakest additional condition you want to require if you want to guarantee the invariant measure? And right, so this is this. And okay, let me very briefly, there was a work of Benjamin and Pavlos who did synchronization by noise for 543 model using like extending our technique with Michael. And now there is a funny thing. So, okay, everybody knows that if you write a heat equation with the term gradient f, then one can write explicitly an invariant measure. What is funny is that invariant measure, so here is you have grad f, and here you have f. So in particular, if your f is not a C1 function, but let's say C 0.99 function, then this is not well defined, but this is still well defined. And so we are working now with Foale and Lorenzo Zambotti, trying to make sense of this equation and show that this equation, so now this is a distribution, right? If this is like, yeah, right, so if f is just a Hölder function. So we are trying to make sense of this equation and show that the Markov process, which makes sense of this equation, has this as an invariant measure. Okay, so thank you very much. And let's see if there are any questions.
Yes, so thanks, Oleg. And yeah, maybe if Davar wants to comment on your questions, then.
May I ask that? Thank you. So I guess for me, there are two questions here. One is about a stochastic differential equation. And I believe Oleg asked if I know existing results on phase transition for that, depending on lambda. I don't. But I think our methods would work in this case.
No, for sure. But the question whether you would get exact like a unique lambda star, such that before you have no, like you have one measure and after you have like, so that there is no gap. So this is the question.
Well, you run into the same problem here that you do in infinite dimensions, that you don't have monotonicity.
Mm-hmm.
Your second question is, so the short answer is no. We do have I mean, we know a lot about our coupling, so it might be possible to get estimates for convergence rates. We just got existence of convergence in total variation is what we did with our coupling, but it might be possible to get some more quantitative information out of that. Yeah. I believe it is possible, actually.
Mm-hmm.
Yeah. Yeah, but we
because I saw that maybe in order to somehow close this gap, so I believe that with our techniques one can show the synchronization by noise, and maybe it can be somehow useful to show that. I don't know.
Maybe.
Okay.
I mean, one thing to be aware of is I mean, you could try to so if you think about the SPD version of your SDE on the second line, so in other words, just W is infinite dimensional Brownian motion, and XT is a function for every t rather than a one-dimensional set of objects. Then, and of course, you have a diffusive Laplacian added. So you can try to scale that equation. So you can try to do a space-time scaling of the equation, kind of like what you do in KPZ theory. So that instead of putting the parameter lambda in front of the noise, you put it in front of the drift term. And what you'll find is that when you do the right scaling, you can certainly do that, move the parameter in front of the drift term. And why you want to do that? Well, as you mentioned in the drift term, or maybe I did, as in any event, as in the drift term, you do have a comparison theorem, which means that if you put a parameter, say alpha, in front of the drift term, then you find that there really is a critical alpha. So if alpha is sufficiently small, alpha being the constant in front of the drift rather than the diffusion, if alpha is sufficiently small, there is a unique invariant measure. If alpha is sufficiently large, it flips the order, of course. If alpha is sufficiently large, there is no unique invariant measure, and there's a critical phase transition. The problem with scaling arguments is that when you do the scaling to put the constant in front of the drift, you change the size of the torus.
Mhm.
And we do know that the size of the torus affects these critical dimensions. So it's really not at all obvious that there is a critical phase point.
Okay, thank you.
Yeah, so there is a question in the chat. So somebody asks, does some similar results known for the Wright-Fisher noise hold?
I think that's a question for you, Oleg.
Oof. I thought it was a question to you. No, I mean, not to me.
I see Yuri has a question.
Yeah, so sort of following up on the size of the torus question. So do you expect your results to hold in the non-compact setting on the entire line? Would you have exponential convergence or something like that too? I mean, I guess you should, but then, I mean, do you have this dichotomy? I mean, anything?
The short answer is we don't know. I should say, I do want to give a little more credit to Zimmerman et al. It's, if you think about what they've done, so they did it on torus, their studies. It's really pretty incredible that by running experiments, you can decide that there are inflating invariant measures, or there's a unique invariant measure. So I don't know how they did that, but presumably whatever they did can be replicated for equations on a non-compact state space. But I wouldn't be the right person to guess the answer. That's just to guess the answer, of course, not to prove a theorem.
Okay, so any more questions either on the
Thank you.
chat or yeah, if somebody wants to unmute themselves and ask something. Yeah, Alex.
So, I guess I just wanted to ask, does, I guess, Devar, your result sort of works, you said for white, like spatially white noise, but then Oleg, you were saying you could handle sort of only finitely many modes of the noise. Does that work for the system that Devar considered also, with sort of less modes being forced?
Sorry, Alex, are you asking me that question or?
Well, I'm not sure who wants to answer it, I guess, but
I would guess that like my hope would be, and I thought a little bit about this, that Devar's result, some of the Devar's result definitely can be passed to the scenario where here you have finitely many modes, and here it's, instead of this guy, you have lambda times u, something like this. So I would say, I don't know what Devar would think. What do you think?
I think so, although this would throw a major wrench into our coupling argument. So one would have to see if the coupling would continue to work carefully.
Okay, so let's insert this.
So we actually use 4 different couplings for the non-uniqueness part. And so there's a lot that can go wrong when you change the noise structure.
No, so my hope that exactly that part of your paper can be simplified with techniques we developed with Mikhail. So this I would hope. But Alex's question is much more tricky because there are other parts of your paper which I'm not sure whether they would go as nice here, like convergence to zero, for example. Is it obvious that if lambda is large and your noise is like this, you converge to zero?
So I would say if the sigmas are bounded,
Mm-hmm.
perhaps, yes.
Okay.
It seems like
Well,
the
maybe
non-degeneracy
not
of the
obvious.
noise. Sorry. It seems like the non-degeneracy of the noise should be most important for the coupling.
But we really need the fact that the noise is actually white in space and time.
Uh-huh.
So our coupling really uses that.
All right. So
Yuri, do you want to ask a question? What is that? Yeah.
Well, it's not really a question. It's more of a comment. So somehow there's this notion of persistence that was developed by Michel Benaim, maybe in a slightly different context, but somehow it's ignored in all this work by Martin. And it's about, if you have diffusion of some stochastic process in some domain, and the question is, does it eventually, in the limit of infinite time, does it does it stay inside or does it go to the boundary? So persistence would mean that the invariant measure is still concentrated in the interior, even if the existence of that invariant measure in the interior, although the boundary may also support an invariant measure. So that's persistence in his terminology. And he and his team, they proved some results in the context of processes with switching. This is why I'm familiar a little bit with that. And so the standard techniques, it seems, so that's of dealing with persistence is using some kind of Lyapunov functions. But in general, this is a it's a long ranging question about even like sort of non-ergodic behavior. If there are several invariant measures and maybe you're not following one of them really, but oscillating between several of them, something like that. But I think it would be just a good sort of bibliographical reference sort of for people working in this area, if it to refer to Benaim, because he developed this persistence viewpoint. That's all I have to say.
okay, thanks Yuri for your comment. And okay, so I guess if there are no more questions, then we end up the session for today. So again, thanks to all the speakers.